Well, looks like we can officially start. Welcome back, folks. We're in midway through week number 5, but the big announcement is congratulations on getting through the exam. It was open to be scheduled between Monday and Thursday, so some people might still be under the exam 1 work. But as far as the grading is going to go for exam 1, I'm going to begin grading them first thing on Friday morning. My hope is to get it completed sometime on Friday, and I should be on track to have it done before the end of the day. But if anything goes wrong, if it takes me a little bit more long to grade that exam than expected, I'll always make sure that any big grading work like this is going to be completed at least sometime on Sunday evening. That's a pretty late deadline, but my goal again is to get it done as soon as possible with the hopes of completing it on Friday. But congratulations on getting through it if you've already gone through it or you're about to. For what we have going on today, this is going to be the very first unit that's going to show up on the second exam. And then after finishing off this unit, we're on the last example. We'll move into the final unit before we change over to chapter 4. But that's pretty much all I have for the announcement so far. Our quiz number 3 is due tomorrow. And this one posted early as before is going to be based off the unit 3 material, 3D rather. So quiz 4 will make a lot more sense, I'd say, probably once we get pretty far into unit 3D somewhere on Thursday. But any questions at all, folks, to start us out today before we get started?
I just had a question about the readings. So I know that on Canvas it does say read Unit 3B February 11th. But going into 3C, I know that we kind of worked into 3C a little bit already, just briefly. Um,
Yeah,
and so I was wondering if we wanted to have like the units read before going into class, is there going to be an update to the reading schedule at all, or is it just going to be on Canvas, as it has been updated?
it'll be just on Canvas, yeah. And actually, I forgot to make an update on this one. I should have said here for the due date on this, due February 18. And that should be the same due dates that you see on the MyLab platform as well. But yeah, as far as the readings, it's not exactly a deadline. This is more the due date that goes along with the MyLab homework system is in particular. And pretty much the best time to do the reading would be to say skim it before coming to class. If you have a lot of extra time, then read it at a higher level. And then after class, if you do another reading of that, maybe at a higher level, doing the examples with pencil and paper out, that'll make the homework in the MyLab go just a lot faster. You'll have a really great idea of just how all those problems go. But does that answer your question about the reading?
Yeah, I think so. Thank you.
Yeah, you bet. And again, yeah, pretty much all these dates that you see here, what I'm trying to do is, looks like I forgot to do it today, is correspond it back to the homework system in Access Pearson, MyLab. Let me open that thing again. It's kind of an adventure opening this up each and every time. And let me double check. As far as Unit 3C goes, the due date is February 11th. But my goal is to have this pasted when I'm absolutely 100% certain we're going to finish it on a particular day and then put a 1 week turnaround on it. So that due date looks like it's official. And if we're on track to finish Unit 3D, I'll place that due date here on the Canvas webpage. That's going to be due February 19th. But if we need extra time, I'll leave it blank so that the next time we'll be finishing off that unit will be when we come back on a week away from today, the 18th. So the due date would be the 25th altogether. So kind of far in the schedule, thanks to the upcoming holiday. Well, thanks for asking about that. Are there questions at the moment? Okay, well, let's visit where we left off before. It's been kind of wild since we kind of paused this unit to review for the exam. Then Monday was reserved for the exam itself. This is where we left off, but let's kind of review and refresh what we were doing before all that stuff, reviewing for the exam and the exam on Monday. This section was all about dealing with uncertainty in the sense of precision, working with the concept of, I'm drawing a blank here, sorry, significant digits. For some reason, I wasn't coming up with that too easily. And finally, after working with significant digits and absolute relative error, we're moving into just the dichotomy of precision versus accuracy. But kind of the warm up on this one is, this is a formula that just got inherited basically from Unit 3A. Absolute error is just going to be the measured value minus the true value. And relative error is the absolute value divided by the true value converted into a percentage through the times 100%. And it's kind of a nice formula in the sense that it does make it come back in just the very next section as well, which is kind of nice to see this stuff not just used exactly once. For the kind of problems that we solved, let's look at maybe part B. We were told that a synthesizer is set to output a standard note A at 440 hertz. So we thought of that as the true value in the problem. Let me zoom out just a touch. So we have the true value here in the absolute error part. We saw that the frequency counter measured the output at 432 hertz. So we took the measured value minus the true value, got the -8 hertz, and divided by the true value here, multiplied by the 100%, and that gave us the relative error in the problem. So we were expecting a 440 hertz, but we've measured 432 hertz. We'd say the relative error is -1.8%, and the negative just saying we're below the target of 440 hertz. Well, that's a kind of fast refresher of what we were just discussing right before turning to exam one material. Any questions at all about example 3 or the concept above? Okay, the last topic on this note of precision versus accuracy is kind of tricky in the sense that we usually think of these as being completely synonymous to each other. In ordinary language, we think precision or accuracy not making any difference at all. But if we're making scientific measurements of some kind, these two words do have a specific meaning. So let's work through these definitions carefully as we apply them to the two examples below. I'll hide part B for just a moment. We'll say that accuracy is going to describe how closely a measurement approximates a true value. So what's kind of nice about this problem is it's using the same language that we had before when we were looking into this definition above. So we're looking at some kind of measured value, comparing against a true value once again. So accuracy describes how closely a measurement we make approximates a true value in the problem. And we'll say that an accurate measurement has small relative error. So relative error makes it come back on this problem as well. Now we've looked at precision before when we were looking into significant digits. Precision describes just the amount of detail in making a measurement, whether we can measure something to say the nearest inch or the nearest hundredth of an inch. It's describing the precision in the problem. So again, telling the difference between the two is a little bit tricky, so we'll look through a couple examples. So think of this as just how precise your measurement value is. So amount of detail in a measurement. And think of accuracy as how close we are to what we should expect to see in terms of small relative error. The smaller the relative error, the more accurate. Okay, so here's our scenario. It says for the pair of measurements, we'll say which measurement is more accurate, which one is more precise. And I just have a couple random scenarios pretty similar to what you'll see in the MyLab homework as well. The scenario starts off by saying, a rookie chef is weighing flour for a pizza dough recipe. The recipe calls for exactly 500 grams of flour, and there's two devices to measure it. a mechanical kitchen scale with markings every 10 grams reads that that dough weighs 500 grams. Then, this is a rookie chef, so maybe unsure of himself, he throws this on a digital scale, and this reads to the nearest tenth of a gram. And on that measurement, it came out as 496.5 grams. So we want to say which measurement is more accurate, which one's more precise. But really, to nail this down, we have to identify what would you all say the true value is in this problem. If we can get a number for true value, then the rest of the computations start to fall into place. So anyone see what the true value should be in part A? Yeah,
Is it 500
absolutely,
grams?
Amy. Yeah, you bet. It'll be what the recipe is asking for, that exact 500 grams. I'll just highlight the figure rather than the exact. So that's going to be our true value in the problem. Now that we have that nailed down, we have two measurements. So we have a measurement of 496.5 grams and another measurement of 500 grams. There's two measurement devices, so we probably want to just kind of split this off into a two-column system. Let's start with the mechanical kitchen scale. I'll just call this kitchen, well, let's call it mechanical to differentiate it from the digital scale. So there's the mechanical scale. For that mechanical scale, the measurement was 500 grams. So we want to see how accurate that was in terms of relative error, but notice the measured value is dead on the true value for this particular case. Let's write it down just to see what it would look like on paper. Relative error would be measured value of 500 grams minus the true value, 500 grams again. We divide by the true value of 500 grams. But this whole thing, even if we go times 100%, is just going to come out as 0. So it's equal to 0% altogether. So we are right on the mark if we're just looking at the mechanical scale. Then what's going to go up the digital scale? It's a little bit short of the true value of 500 grams. So we would say on the digital scale, we made a measurement. It measures 496.5 grams. So the relative error on that is not 0%. That's a bona fide calculation this time. So let's put down relative error. Let me try to save some space by going this way. Relative error is going to be measurement of 496.5 grams minus the 500 grams. Divide by 500 grams once again. The relative part means percentage, so we'll go times 100, keep the percent symbol. And now we're just back to the end of the calculator. Let's see what we get on this. So 496.5 minus 500, division by 500, and now times 100 for the percent, tells us we're off by less than a percent, negative 0.7%. So is that a big deal? I'm not sure. I'm a rookie chef myself. I'm not sure if that's going to mess up the pizza or not. Maybe it depends on how it's being cooked, what toppings are going to go on that, what the customer expects. But the error here is significant. So that would tell us, according to the mechanical scale, it's more accurate because it's closer to the true value in terms of relative error. But let's move on to the precision side, and then we'll just make one overall statement. to address which one's more accurate, which one's more precise. So as far as precision goes, the precision for the mechanical scale, it says, well, it has markings on every 1/10 of a gram. So we might say the precision on this one is 10 grams. Or you might say the nearest 10 grams would be a great way to convey it. The precision on the digital scale, well, it's to the nearest 1/10 of a gram. So 0.1 grams. That means, although the mechanical scale is more accurate, it has a smaller relative error, the digital scale is more precise. So saying that all together in one sentence, we can say the mechanical scale is more accurate and the digital scale is more precise. Well, that's so far the breakdown of accuracy versus precision. Any questions at all, folks, getting through that first part A?
I have a question. So,
Yeah.
did we really, do you have to calculate the relative error when it said that the markings were every 10 grams and that the other one read to the nearest 0.1 gram? I feel like that kind of told us right there. But is it important to do the calculation for relative error?
You know what? That's a really great question. It turns out I'm just following the definition of the book pretty much verbatim for kind of a tie in what we saw here. This is how our author wrote the definition. But if you didn't use relative error and all you used was absolute error, that would have worked just fine. Absolute error would have given us 0 grams. Absolute here would have given us negative 3.5 grams, and we'd have made the same conclusion. The mechanical scale is more accurate, and the digital scale is more precise. So absolute error also works for these problems. Was that the major heart of the question you were asking?
Well, I was kind of just looking at what it told us in A, because it looks like we really, when you're talking about the precision, you took it directly from the problem. So I
Yeah,
was wondering, what was the purpose of doing the math for it?
the math for is more for the accuracy specifically. It's pretty plausible that, say, maybe in just a different problem, something in my lab homework, that the mechanical kitchen scale, let's say it came out to for 90 grams for, like, say, a totally different problem. Then the absolute error would have been negative 10 grams here. The absolute error on this one would have been negative 3.5 grams. So we would have said this one is more accurate if it read 490 instead in the measurement.
Okay, I understand now.
Awesome. Thanks for asking about that. And honestly, I think that's a good one to just put down on notes for the sake of what if? What if the problem was different? So let's take this. And just for the sake of let's say in a different universe, we had a whole different problem and it went this way. Let's put this down in the notes here. If this was, say, 590 grams, then we would have gotten 590 grams here. And let's suppose we still did the relative error, the percent part of it. This would have came out as 590. Excuse me, not 590. That's way off. I was thinking 490. I'm really kind of making that rookie chef look bad. He got to 490 grams here and 490 grams here, just say for the sake of a whole different run on this problem. Then the relative error would have been 490 minus 500. divide by 500 times 100. So we'd be off by 2%. So in this case, the relative error is pretty bad, and we would have said the digital scale is more accurate because it's only off by less than 1%. The smaller the value, ignoring the positive or negative sign, the closer to zero, the more accurate it becomes. And the other part you mentioned, we can just directly read off precision by what it tells us it reads to. The smaller the value, the more precise. So the digital scale would still be more precise in this second run of the problem. Other questions with that so far? Okay, so again, back to this comment right here. If you didn't calculate the relative error and you're just looking at absolute error, that actually works as well. So small relative error or absolute error will still give you accuracy in the problem. Relative error is just kind of more interesting because we can just see what percent off we are based off the true value amount. Well, maybe one kind of question that's kind of interesting when you do a problem like this, we see the mechanical scale is more accurate because it's dead on 500 grams. The digital scale is more precise only because it reads to the 10th gram. And if you're that rookie chef and you made the two measurements, you have 500 grams on the mechanical scale, sorry, I was on the wrong part of the sentence, 496.5 grams on the digital scale, you might wonder, well, what should I do? Which measurement device should I go by? And that's got a pretty big what if kind of question. What should the rookie chef do? Well, I would say maybe double check that digital scale, make sure it's calibrated, make sure he hit the tare button, all that kind of stuff. And in the end of the day, if it's off by less than 1%, I would just go with what the mechanical scale would have read as. Well, there's lots of interesting things to think about with this one. We'll do another part B to this just to see how it goes together. But any last questions or comments? Okay, so for a whole new different kind of scenario, we're looking at true heights. So we're imagining maybe you're with a friend at a doctor's office because it said your friend, and perhaps someone happens to know that your friend's true height is 62.55 inches. Not exactly sure how we would know that if we were wondering if these measurements are accurate enough, but assuming we somehow know that figure dead on, we're going to work with this as being the true height in this problem. And it has the same kind of drama like in the last situation. There's two different measuring methods that we can take on this. Standard measurement will be the tape measure. We have a tape measure that can be read to the nearest 1/8 of an inch. And there's nothing wrong with 1/8, but I think it's sometimes convenient to see that as a decimal number. Let's throw in that in. The measuring tape is precise to 0.125 of an inch. So that gives us a value of precision on this one, 0.125 of an inch. And using that measuring tape, the friend's height reads 62 5/8 of an inch. So that's one measured value. And here's where it gets interesting. It says a new laser device at the doctor's office. I've never personally seen one of these. That gives readings to the nearest 0.05 inch, 100th of an inch, measures your friend's height as 62.45 inches. Well, it's another measurement. So let's say we have a height measurement by the laser device. Hopefully it doesn't hit you in the eyes. Maybe close your eyes when that's working. But it has this amount in precision. So, you know, at this moment, we can answer immediately what the precision is, and then we'll come back and analyze the accuracy. So the most precise device is, anyone see what it is? Is it the measuring tape or the laser device?
The laser.
Yeah, the most precise one is the one that has the smallest value that it can read to. This one is to 5/100ths of an inch, whereas this one is a tenth and some change. So quite a bit more than twice this value here. So we'll say, is the laser device? So with that out of the way, we can now look into which one is more accurate. And we did the last problem just doing the relative error. Again, we were following the definitions verbatim, but let's focus on absolute error just to emphasize that's another fine way to answer this kind of question. The most accurate method has the smallest absolute error, and totally fine to calculate it in relative error. So I'll say, or relative error, how we did the last problem. So here's where we want to break it up. We have first a tape measure. I think one of the ways this problem it gets kind of tricky is there's a lot of information everywhere. So if you can start organizing into a two-column system, take the tape's measurement. We have a measures 62 plus 5/8 of an inch. Here it is as a mixed number, but that makes me slightly uncomfortable. I would probably write it this way because that's what's going to go in the calculator when we convert it down. Then continuing to organize, let's say laser device. Sounds awesome. But with the laser device measurement, this friend measures 62.45 inches. Okay, so assuming that the true height is 62.55 inches, again, that's a big assumption in the problem. If we change the number, we'll change our conclusion on the accuracy. But if that's true, if that's real, we can now determine which one is more accurate. We already know which one is more precise. So let's look into absolute error for this one. Absolute error is going to be the value that we measure. Let's put that into a calculator and then put it on paper. 62 and 5/8 is 62 plus 5/8 altogether. So 62.625 inches minus the true and exact height that we somehow know, 62.55. Let's throw that in the calculator as well. So I have this 62 plus 5/8, that's the number in blue, minus 62.55, the number in green, gives us an absolute error of 0.075. Let me double check my numbers on this. Okay, so pretty small absolute error. Now, I think both of my problems are kind of interesting in a certain sense where the device that's more precise is not necessarily the most accurate, but this is not to convey that's how it always goes in the homework. It's really kind of random, and it depends on what these two measured values are, and extremely critically, what the true value was as well. But let's look at this again, absolute error on the laser device side. This one will be 62.45 inches. Subtract the true value, 62.55 inches. And in the calculator, just to be real sure I got it right, let me put in 62.45 minus 62.55. and I'm off by negative 0.1 inches. And that deserves a double check on the numbers, 62.45, my 62.55. Yep, down by negative 0.1 inch. I mean, I probably should have been able to do the mental math, but it's good to be sure. Arithmetic is the first thing that goes when you're tired. But now that we have the two numbers, anyone see which measurement system, the tape measure or the laser device, that would be considered more accurate?
The tape measure is more accurate.
Yeah, I agree. The value here is smaller, ignoring the sign, positive or negative. This one's closer to 0 than this value is. So that makes the tape measure more accurate, absolutely. So let's say here, this shows the tape measure is more accurate, since it has the smallest smallest absolute error, which is what we calculated on this problem. Yeah, absolutely, Zach. The tape measure would win as the more accurate. So it kind of was the same problem in a certain sense, right, as part A. In part A, just like in part B, the laser device is more precise. The tape measure came out to be more accurate. You could say that the laser device is precisely wrong in the sense that the tape measure was the one that's more accurate. And again, you might wonder if you're, say, the nurse doing the charting on this, which one would you trust? Possibly the tape measure might be a good idea because this is a new laser device. Maybe it's being used wrong. Maybe it didn't know where the hairline started or something going on like that. Could have been some kind of error that went on when the measurement was made. And so as far as the values we see here, the precise one, once again, is the one that has the smallest value right here that it's accurate to. And the most accurate is the one, whether in an absolute error or relative error, has the smallest error altogether. And I think the negative signs, again, are a distraction for this kind of work. We're thinking in terms of just positive or negative. The one that's closest to 0 is going to be the most accurate. So that's why this one won. Well, that's the entire conclusion to Unit 3C. We did a lot of things on this one, working with things along the lines of significant figures, order of magnitude came into play, and then it ends on, this is just an additional topic, thinking about absolute error with precision and accuracy. Well, any last questions or comments, folks, before we take a look into the last unit of Chapter 3? Okay, well, the last unit of Chapter 3, I think it looks kind of gnarly the first time you open up the notes. There's new definitions, a whole bunch of tables. But if you think in terms of, it's kind of another rundown of working with percents in just other clever ways. And this formula actually makes a big comeback, relative error, it's used again. It's really not too bad of a section or a unit. We'll go carefully with this one because, again, with all the new definitions, all the tables that we're going to see in this, it is one of those units where it's easy to get kind of lost. So as usual, I try to match up the problems pretty strongly with what we're doing in notes and what's actually going to be listed in my lab exercises. My numbering's a little bit off because I called this example 1 with 4 parts, but this would be like problem 1 in my lab. This would be problem 2, problem 3, problem 4, and so on. So we're looking into index numbers, and then we'll get into CPI, the Consumer Price Index. And beyond, we're going to look into the federal minimum wage. So that'll be another table across the years and decades. The first thing we have to define, whether we're talking about CPI or anything else, is index numbers. And the definition is really nice in a certain sense because it's not really doing anything too different than what we've done before. The idea is we're just using lots of percents at once to make comparisons. The definition says, an index number provides a simple way to compare measurements made at different times. And so we have across several decades here, the price in gasoline per gallon. If we convert this this price as a percentage of the 1990 price, we'll have loads of percentages, but we're going to think of this as an index number. The value at one particular time or place is chosen as the reference value whenever we're thinking of index number. And this is our reference value in this problem, the 1990 price. That's a pretty good reference value because gas prices exploded sometime between 1970 and 1980, and it kind of stabilized before it started to get larger and then exploding again a little bit in 2010, just looking into the decades rather than particular years. So when it says reference value, this is our reference value for this table. So to compute any index number, it says the index number for any other time or place is take the value, divide by the reference value. Our reference value is going to be the $1.23 to correspond to 1990 and go times 100. And that looks kind of funny in a certain sense. If we go back to say this unit 3C or maybe unit 3A, the only thing that's missing, let's maybe leave that 3C there. The only thing that's missing with this formula is the actual percent symbol's gone. But we're really still looking into percent. We're just not putting that percentage symbol on if we think of it as an index number. So peel off the percentage and you're looking at a relative error, for example, as an index number. And the reason we're doing both the percent and the index number is just to think of that big change here as we're going from percents to indices or indexes. I think indices is the proper plural, not indexes. So our reference value is 1990, and so that means it's going to be the $1.23 amount. If we complete this table, as Part A suggests, we'll have index numbers across the decades, but this index number right here is the one number that's a given. Let me make this a little bit bigger so we can kind of fit this in without cramming in the numbers. Kind of write big, personally. Well, let's follow this formula, see how it goes, starting with 1960. So we can say the index for 1960 is going to be the value. The value it's referring to is the 1960 value in price per gasoline per gallon. I'll write this in as just the 31 cents, with understanding it's a 31 cents per gallon. Then we divide by the reference value, so we have to look into the particular year in question, 1990, so divide by $1.23. And if we take this and go times 100, that's our index number. So let's read this in. We've got 0.31 divided by 1.23 times 100. Our index number is then 25.2, but that's the exact same as the percent. It'd be 25.2%. And we're going to round pretty much all of our values, whether they're percents or indexes, to one decimal place in this entire section. So I'll go 25.2. That's a percentage. Usually this column isn't normally here for thinking index numbers, but it's here this one time, just like in the reading, just to tell the difference between the index. The index is 25.2. Well, nothing too earth-shattering, right? When we're thinking of index numbers, we're just taking off the percent sign, but we're doing the same kind of strategy that we've been doing in, say, Unit 3A. We could say that the price of 31 cents per gallon is 25% of the 1990 price at $1.23 per gallon. Or if we're making lots of comparisons at the same time, we would just say the 1996 reference number, or excuse me, index number is 25.2. We'll complete the table to get all the index numbers, but we'll always see this matchup from percent to index. Well, any questions at the moment, folks, with getting row 1 done?
I know that this one is pretty straightforward in determining the value, but in questions in the future, are they going to tell you what the value is to look at, or is that always assumed to be the first value that you get?
So are you referring to, say, the reference value, the $1.23?
No, the first value where it's just value.
Gotcha. Yeah, so we would have to assume that when we say value, if we're getting, say, the very first percent or index, we're always going to be referring to those values in the table right there. But then the value is going to change. We have to do the same index computation for all of those values at once to get all of the indexes down the line. But I think a good way to think of it is the value is always what goes here. So that's always going to be in the numerator when you do the index computation. Does that make sense with that question there?
Yeah, I get it. Thank you.
Yeah, absolutely. Thanks for asking about that. So yeah, they have to be specific about the reference value, but then the value itself, we're going to do 1, 2, 3, 4, 5, 6 more computations. So it's kind of a good calculator practice on this one to get through it. Other questions so far? Okay, let's put down just a couple more pieces of scratch work like we did here, just to show how we're putting this together. So now if we're doing row 2, getting either the percentage, let's focus on the index. We can say that the row 2 index is going to be, first the value, 36 cents per gallon. So 0.36. Then we divide that by the reference value, $1.23, corresponding to 1990. Go times 100, and we have our row 2 index that would go right here. Now, in the calculator, let me dismiss that, that's weird. All we're really doing is changing the numerator. The denominator, $1.23, always stays the same. And so a lot of calculators, you can press like an up arrow button, call the last thing you did, and just scroll over to the left, change this one to now 0.36. Then that's our next index. To the nearest tenth, that's 29.3 as an index number. As a percent, 29.3%. And now we're kind of down the line. This is close to 1/3, so we could say the 1970 value of gas per gallon was just under 1/3, which would be 33.3 repeating the 1990 value of $1.23. So let's do this again. Same idea, but different year. Just figure out where to park the calculator. For the 1980 value, this is where people kind of panicked in the global economy when the gas price per barrel just skyrocketed out of nowhere after being stable for decades. It came out to $1.22. And for the first time in people's lives, the dollar number went faster than the gallons number when they were at the pump. So 122 over 123 times 100, that jumps the index number to 99.2. As a percentage, 99.2%, very close to 100% of the 1990 value, stabilized from 1980 to 1990. But there's a bit of a trick with this table. One row is actual freebie. When we had a reference of 1990, it told us this one is automatically 100%. And the index here is just automatically 100. But we can run it through the formula and see. If we change the value to the 1990 value, we're changing to $1.23, and that's where the 100's coming out as. The 100 isn't anything too special or specific, except that it tells us that this is the row where every other index number is being referenced off of. So this is like the major pivot point of the table where all comparisons are being made from that 1990 value. So we'll compute three more rows just to get the table finalized. But any questions so far with any of these numbers? Okay, now for the 2000 value. Again, it was pretty stable. It's going up, but that might be just ordinary inflation. It was $1.56. And now our index number is beyond 100. We have 126.8 or 126.8%. So this is now telling us that the 2000 prices are 1.26 times the 1990 prices. Then it blew up again, 284, almost doubling. Not as bad from 1970 to 1980. That was almost tripling in a certain sense. Excuse me, almost times 4. Here it's almost doubling, times 2. So next row has a new value that we'll place in the numerator here. Put in the 284 price per gallon in 2010. This is an average across USA for the year 2010 specifically. 284. Now the index number is 230.9. So 230.9%, more than double the reference value in 1990. And something strange happened from 2010 to 2020. It actually dropped. That was really due to COVID. The entire global economy went into a slump. Price per gallon went way, way shockingly low for a minute there. And that was a pretty crazy price for a little while in 2020. It's back up. It's around 286 in Idaho Falls, roughly, when I wrote the notes at least. So the index number in 2020, we'll take the 217 value, divide by the 1990 value of $1.23, go times 100 to make it an index. It's 176.4. As a percentage, 176.4%. So that's what's going on with index numbers in this kind of table here, looking into comparisons of gas. So with 1990 as a base year, we can see how gas became more expensive, more than twice the value in 2010, and then dropped a little bit. If we go backwards in time, we see it's not too different in 1980, but gas prices relative to 1990 really dropped by a lot, almost 25% of the 1990 value if we're in 1960. Well, any questions at all, folks, with index numbers at the moment? Okay, once you have a table like this set up, you can now ask and answer pretty interesting questions down the line. It says, assume that the current cost of gasoline in Idaho Falls is $2.86 per gallon. It did recently drop under $3 per gallon, which was kind of amazing. It'd been up there for quite a while. It says, find the current price index number using the 1990 price as a reference value. Now, part B is not too different. We're just saying, what would the index number be based on a 286? So we can say the index, we use this as the value, the 286. It says still using 1990 as a reference, so we'll divide by the 1990 value, $1.23, times 100 makes this an index number. So only change is in the numerator, 286, and we get an index of 232.5. So it's interesting to know that that index number is the largest index number on the screen right now. It beats every number, 2010 just barely. Every single index number is beaten by the current cost of gas in Idaho Falls. Again, that was looked up, I think, on Sunday of last week, so that's probably already not quite accurate any longer. Any questions at all, folks, on just this follow-up index computation? Okay, another big value of having a table like this is, here's a pretty interesting question you can now ask. Suppose you were driving a car where it took exactly $20 to fill that tank. But in 1990, we're wondering now, how much would it have cost to fill the same tank in the year 2020? So we're kind of looking into what is the value of that full tank in 2020 dollars. We can use this table to answer this kind of question and see just how much it's going to cost at the pump. What we'll do is take the $20 value, and we do this kind of multiplication here. We go times, actually, let me give this a name to start out. Let's say amount to fill, meaning fill the tank, in 2020. It's going to start with the 1990 value. So I want to write this out as a formula in a format of a formula we're going to see later. We take the 1990 value and we multiply it by, take the index for 2020. I'll write this as 2020 index, and then we divide it by the 1990 index. So there's a pretty strong matchup in this formula. If we're talking 1990 value in any computation like this, we want the 1990 index in the denominator. So now we can look up the values from the table that we produced above and say that this works out as the 1990 value. I'll write as, again, just $1.23 with the assumption it's $1.23 per gallon. Or hang on, getting a little bit mixed up on the index. What I wanted to take was this being the 1990 value. Sorry for the backtrack on that. I want to use the $20 right here. My arrow is going to help my mind see that better. So $20. Now we're looking in terms of the indexes. So take the 2020 index. The 2020 index was 176.4. Divided by the 1990 index, and that 1990 index was, let's see here, exactly 100. So if we change the base here, say we said maybe it took $5 to fill the gas tank in 1960, our denominator would have been a 25.2, just a different index number. So with those two values in play, we can now see how much this is going to cost. Take $20 times 176.4. Divided by the 1990 index number of 100, and it comes out to $35.28, which is about how much it cost me to fill my tank, roughly. So that's a kind of interesting computation, and this is pretty much the spirit of what a lot of our questions are going to look like. Looking at the value of the dollars in 1990 versus how much they would be in, say, a different year, like 2020. Does that make sense on that computation there?
For questions like that, do we not round up to the nearest decimal unless it specifically says to, or do we just write it as it is?
Oh, you meaning to the nearest decimal, say the 2 right
Yeah,
there?
the nearest decimal. That's what I meant. Sorry. Yeah.
Yeah. You know, following this verbatim, I really should have rounded this to $35.30. But I think for any time it comes out as money, probably the best advice is always just to round it to the nearest cent. So 2 decimal places in this one time. And MyLab is really pretty specific about that. When you go to put in the answer, they'll just say right down below, if it's money, round to 2 decimal places in that kind of case. But you know, if this was an exam question and I said round all values to 1 decimal place, $35.30 is completely acceptable as well for an answer. Does that make sense with that question there? Any other questions so far? Okay, here's another pretty interesting follow-up question down below. It says if it cost $3.50 to fill a gas tank in 1970, and 1970 they had it kind of nice, what percent of the same tank? So let's imagine we're driving the same car from 1970 in 2010. Maybe your friend is a mechanic and they're just helping you out, keeping it up to shape. What percent of the same tank could be filled with $3.50 and $2010? And using the table above, we can make that computation as well. Here, we're more interested in the first two columns, the year and the price of gasoline. The index numbers made a really big showing in a problem like Part C. But Part D is a little bit different kind of a question. Let me paste this table down below here for easier reference. So we're being told it cost, I think we need a new page on this one. Let's just drop it down. It cost $3.50 to fill a gas tank in 1970. So we want to know what proportion or what percent of the same tank is filled by the same $3.50 in year 2010, where the cost of gasoline has skyrocketed by this table from 1960 to 2010. It's a tough question because we're asking about the percent of the tank filled, and it's a reasonable question. But now it begs the question of how big it was that gas tank in this car when we filled it with 350 in 1970. So let's start by saying the size of the tank, short for gas tank of this car. $3.50 filled this tank. So we take 350, but then we can find the size of the tank if we use the 1960 number of 31 cents per gallon. It becomes a unit analysis kind of question. What would you all say that we have to do in this problem? Should we divide or multiply by the 31 cents?
You'd probably divide, but it's asking for the 1970 number.
Oh yeah, thanks for spotting that. I was going to divide by the wrong figure. Yeah, absolutely. Good call. We have to divide by that figure there. So we go divide by 0.36. And it doesn't look right because now units are going to cancel. And we want the size of the tank in gallons. But remember, this was just a shorthand in the table. This was, wrong number again, 36 cents per gallon, in fact. So if we say 36 cents per the 1 gallon, here's the entire fraction we're looking into. 350 divided by the fraction, 36 cents per gallon. If we keep on going with careful unit analysis, here's what we'll get next. $3.50 to fill the whole tank. When we're dividing by a fraction, we have to now flip it, take the reciprocal. So go times 1 gallon, divide by the 36 cents. And this looks right. We're going to cancel a unit of dollars. We're left with just a unit of gallon. So we're getting to our target on this one. So all we're going to know is the size of the tank on this car. Keep on grabbing the wrong thing. Let's take 350, divide by 0.36. And again, you could have just done that immediately. 350 divide by 0.36, get this figure on paper just right away. But doing this unit analysis is just a way to be sure it really was divide. It cannot be multiply whatsoever. The unit would have come out completely different and wrong. Well, we're going to write our final answer to the nearest 1/10 of a percent, but this is a computation in the middle. So for the sake of accuracy, I'll keep 4 decimal places on this number. So 9.7222 gallons. Again, a lot of accuracy just so that our computations in the middle don't round too much and introducing too much inaccuracy. So that's the size of the tank in gallons way back in the day. And now we're wondering, how much could we fill with that same $3.50 in 2020? Well, we can find out that number in gallons as well. Let's say here, amount filled in gallons. Remember, this is the same car with the same capacity, but this is going to be the amount filled in gallons after spending $3.50. But now we're in 2010 rates in 2010. So the amount filled will take the $3.50 just like before. But times have changed since the 70s a lot. We're now dividing by $2.84 per gallon, $2.84 for the 1 gallon. So same pretty much setup, $3.50, except we're taking times 1 gallon, divide by $2.84. Really, our only difference here is the denominator from here to here. Units cancel in the same way, just like before. And here's what we have this time. This is going to tell us how many gallons we've pumped. 350 divided by 2.84. We've pumped a measly 1.2324, rounding to the same place in terms of gallons on that 350. 1.2324. Gallons. So that's pre-start. We're assuming that this 1970 car has a capacity of exactly 9.7222 gallons. So that's kind of a small mathematical fiction, but if we imagine that is exactly the reality, that it was really filled by 350 in 1970, we can now answer the question of what percent of that same exact tank was filled by 350 in 2010 using the 2010 rates. Now it's just an overall percent question. We can take this number here, divide by this number, convert it into a percentage. But these two computations in the middle, I think, are the tricky ones, just getting started. Any questions at all, folks, getting either of these two numbers? Okay, so going to the original addressed question, we can say percent of tank filled. This is in spending 350 in 2010 is going to be, well, we pumped this many gallons, 1.2324. We're talking about the percent of the entire tank filled, and that's the entire capacity, 9.7222 gallons. It's a what percent question this time, so it's not an index number. That means we'll go times 100 and keep the percent symbol. Units should always cancel for doing a percent like this, so it's nice to see gallons and gallons gone. And one last calculator computation to finish off part D. We'll take 1.2324, divide by 9.7222 times 100, and that's our figure. We're rounding this one to 1 percentage point, or excuse me, 1/10 of a percent to get 12.7%. Again, the story is kind of told here when we look at these index numbers going from 25.2 to a blistering 230.9 in 2010. But this just tells the different story, the different perspective. We're visualizing the gas tank completely filled by $3.50 40 years ago, but in 2010, not even 15% filled, just barely over 10% of it. So you're not getting very far, probably not completing the work week on that car. Well, any last questions, folks, on running through this computation? Okay, the big takeaway is these are lots of interesting comparisons we're making all at once. We can ask questions of how much value do we get in 1 year, or a lot other questions along the lines of how much is $20 in terms of a 2020 value, filling up or how much you would spend filling up a tank or pumping $20 worth. We're going to turn this all around when we look into the consumer price index table, this one down below. This is what we're going to be looking into when we come back on Thursday. The consumer price index is just other index numbers that we're taking a look into, but this is in the news all the time because this consumer price index table is what's used to calculate inflation on a year-by-year basis. It's based on the average of prices for a sample of more than 60,000 goods, services, housing costs. It's computed and reported monthly, and these are just the average consumer price index numbers for various years. So we're going to use this to look into things along the lines of the median household income was $23,620 in 1985. How much would that have to be in 2025 to maintain the same standard of living? So these become really interesting and practical questions. And we'll do even better. We're going to be able to say what was the rate of inflation from 1 year to the next. And we'll see how to adjust prices for inflation. We've in fact used this formula once, but here it is in its full stated form using the consumer price index. We'll take some time to really kind of delve into this table, get through the examples. So this will be our stopping point for today's class. But any last questions or comments at all, folks, with what we've computed so far today? Okay, there's a lot going on with this table because it says it's a consumer price index table, 1982 to 1984 equals 100. That probably feels a little bit different from our last table. So we'll see how this index of 100 here conflates with a range of values having an index of 100, and then get started just working with this table, answering some pretty interesting questions. But have a great night, folks. We'll be back to working through this on Thursday's class. Take care.
Thank you.
You bet. Have a good one.